طيب بسم الله الرحمن الرحيم. So last time we talked about IP addressing and we talked about IP version 6 and we talked about the migration strategies or the deployment strategies for IP version 6 regarding the tunneling. We discussed the issues related to tunneling. So this week's lecture is regarding the routing algorithms. So we need to discuss the different routing algorithms, not the routing protocols per se, although we will highlight some issues related to the routing protocols. These are the routing dynamic routing protocols. We'll not cover them in details, by the way, but I will just give some idea about these routing protocols as we discuss the algorithms. So routing algorithms are classified into link state and distant vector. So we'll talk about the difference between link state and distant vector. So the best way to understand how routing works, as we have explained before, is to imagine yourself like going from one node to another, or going from one location to another. So you're going from your house, you're driving to QU. So on your way, you have to go through some intersection or some roundabouts or something like this. So imagine the router being like a person standing in the intersection. So you ask that person, how can I go to QU? So he or she would tell you, go left, go right, go straight, and so on. So this is what we refer to as packet forwarding or one-hop forwarding. So that's what the router does really. So, but in order for the router to make that decision, routers, they need to coordinate to get some routing information about all the nodes in the network. And that happens using two different concepts or two different mindsets. One is called link state, and we'll talk about what link state is, and one is called the distant vector. So that's what we need to discuss. Of course, hierarchical routing is nothing but you do routing in two levels. Each level can take one of these forms, okay? So we'll talk about this as a later stage. Type. So as we have said that this is the interplay between routing and packet forwarding. So routing is to know the entire route, okay, from one node to another. From one location to another, you need to know the entire route that the packet or us as human, if we want to go from one location to another, what is the route to go from one location to another. And that's similar to, like, for example, Google Maps. So in Google Maps, you ask Google Maps, I want to go to that location. So Google Map can tell you, go left and then go right and then go straight and then go to this highway and so on and so forth. That's what routing is all about. Packet forwarding is the process of the router forwarding the packet to one of the output interfaces, and that depends on the destination address. So in the header there is the destination address. Based on the destination address, we decide that this packet needs to go to this output interface or this output interface and so on. Each of these router ports, they have IP address and they have also physical address, of course, and they are stored in the routing table. So the routing table here maps destination addresses to specific output port number. And this output port is the physical address of that port. Type. So this is the interplay between routing and packet forwarding. So now we need to talk about the route. In order to establish a route between one node and the final destination, of course, we have many possible ways to do that. Right? So, and we need to figure out what is the shortest path between one source and one destination, right? So that's the route end to end. And of course, for routing, we need to have the path with the lowest cost. Okay. So the best way that we need to do that is using some graph abstraction. So graph theory or graph abstraction is used in many disciplines. So you can, for example, use graph abstraction for مثلا peer-to-peer network. For peer-to-peer network, by peer-to-peer here we mean that any node can establish a TCP connection to any other node. So by establishing this logical connection at the application layer, okay, so we can have some peer-to-peer session between any node. And that's agnostic to the underlying topology of the network. So we don't care about the physical topology of the network, right? So we can also use graph abstraction to also model the peer-to-peer TCP session establishment, مثلا, right? So in that case, the coast here would model, for example, the TCP coast between two peers, okay? Regardless or agnostic to the underlying topology خالص. Also طبعا يعني similarly graph abstraction is used by Google Maps. Graph abstraction is used in many disciplines. ماشي. So for graph abstraction in the case of routing, what we do is that we model the routers as nodes and we model the links as edges. Any point-to-point link between any two nodes is modeled as edge. So a graph is a group of nodes and edges. ماشي كده؟ طيب, and each edge will have a coast. This coast can be modeled in different ways. For example, the coast can be by default 1, which means that the point-to-point link between the two nodes has a default coast of 1, which means that it's one hop. So all we need to have is to count the number of hops, and we find the path between one node and the other node such that the number of hops is minimum, right? And in that case, this will be the shortest path. But this will be very simplistic and primitive, right, as you can imagine, because not all the nodes are similar to each other, right? So some nodes are very high bandwidth not all the edges are similar to each other. So some edges, they are, very high bandwidth links, like مثلا fiber optic links مثلا. And some other edges, they can represent like a wireless network or wireless ad hoc link, which has very low bandwidth and very high probability of error and so on and so forth, right? So simplistically using like 1 for all nodes regardless of their characteristics is really primitive. But this is in fact used in dynamic routing protocol like what حد فاكر؟ Network 2. By default, there is a dynamic routing protocol that uses by default 1 for all the edges as a default coast. Dynamic routing protocol. Dynamic routing protocol. REP does that. REP, routing information protocol, it uses a coast of 1 on all the links, regardless of any characteristics. But REP was actually used in the past, way in the past. It was the early days of the internet, REP was being used. But later on, of course, as the topologies become more and more sophisticated, REP has become really obsolete, and they use بقى OSPF and EIGRP and الحاجات اللي احنا درسناها المفروض في نتورك 2. ماشي كده؟ طبعا in reality, the coast would represent, for example, the مثلا in highway. As you can imagine, in highways, always Google Maps, they prefer to have you go through the highway, right? The cost for going through the highway is less, right? That's because of what? Because of the fact that in highways you have very high or wide lanes, and this means that the probability of مثلا jamming or bandwidth is high, so you can go very fast, which means the cost is less, right? In other words, the cost is inversely proportional to the bandwidth. صح كده? So as the bandwidth is goes high, this cost is lower, right? The cost can represent actually the delay, or the amount of delay that you encounter when you go from one node to another. As the delay goes high, the cost goes high, right? So in that case, you want the shortest path with the minimum accumulated delay end to end, right? The cost may actually represent, for example, the reliability of the link. What is the probability that this link will مثلا go into errors or disconnection or something like this? So the cost can be one of these يعني matrix or a combination of them. ماشي? So in general, the cost can be a combination of delay and bandwidth, reliability, and other things. Okay, كده? In any way, so we can measure that cost, and we set the edge cost. Once we do this, then what we need to do is that on this graph we need to identify what is the shortest path, and by shortest we mean the path with the minimum total delay, total cost between one node and another node. So that's what so once we do this and we have this graph representation, it becomes easy for us. All we need now is just an algorithm that allows us to calculate the shortest path from U to Z. Like for example, we can do that visually now. So which one is the shortest path here between U and Z? Right, so U, X, Y, Z, that seems to be the path with the minimum accumulated or total cost. Okay, we can do that visually, but we need a systematic way with طبعا يعني some complexity, low complexity, to allow us to derive this conclusion systematically and algorithmically. Type. So as we said, the cost between any two lengths is either the cost between lengths that are physically connected to each other, or the total cost between the lengths passing through other edges, okay? And that cost may not be the shortest path or may not be the minimum cost, right? So we need a systematic way to derive what would be that minimum cost. So the cost of a path that contains these nodes is actually the cost between x1 and x2, and then x2 and x3, and so on. So that's easy. And we answer this question, of course. طيب. So that's what we need for routing algorithm. طبعا routing protocols and algorithms are يعني categorized in two different ways. This one is easy, of course. This one is easy. So we know the difference between static routing and dynamic routing. By static routing here, we mean that there is a person, okay, a network analyst, who actually connects to all the routers, تمام, sequentially كده, and he embeds all the routes manually in each router. Okay? So which means that if I have a topology, a specific topology like this, okay, so that person would go here, and then he would say, okay, so if I have any address with this subnet address, okay, all these group of destination addresses, they would go to this hub, or all other nodes, or all other addresses, they would go through this hub, and so on. And then he would connect to this one, and then he would do that manually on every route. Of course, as you can imagine, this process is very slow. Not only that, this process is actually cumbersome, especially if we're talking about the fact that this topology might change. If the topology changes, the network analyst has to go back to all the routers and adjust all the routes manually again. Of course, this is not practical. But static routing is used when the network is very small. Usually, مثلا, they use static routing in a very limited fashion. Like for example, we have a network that has مثلا OSPF running and stuff, and we just want to connect this network with Uridu through like some default gateway in QU. Okay? So we can set the default routes in the routing tables of some of these routers manually. So we can set that manually, okay? Because all of them, they will have to go through one default router anyway. So that could be done. But if the network is large or dynamically changing, this will be very problematic, and we cannot afford actually using static routing. Instead, dynamic routing relies on the fact that these routers, they will have to exchange some automatic messages. We call these messages routing or control messages, right? So these messages will have to flow in a certain way, okay, to allow these routers to automatically construct the routing tables inside them. So each of these routers, okay, using these messages, they will have to analyze these messages and then construct the routing table automatically, okay? طيب, based on dynamic routing, there are lots of issues related to how do we send these messages, what these messages will contain, how do we recognize that when to send these messages and when not to send these messages, right? When do we stop? Okay, what is the complexity of these messages, and so on. Type. With that, there are two possible ways to exchange these messages. One is called like global view, or what we call link state. ماشي كده؟ So global or link state is based on the fact that each of these routers, they will need to know the state of all the links in the network locally here. So each router has to form a global view about all the edges or all the links in the network. ماشي? That's step one. So step one, so for global, step one is get global link states of all the edges in the network. But we don't need all the link states for the routing table, right? So for the routing table, we have step two. We run اللي هو بنسميه Dijkstra's algorithm against the link state global view to create the routing table. So we have to do it on two steps. So the good thing about link state routing protocols is that every single router will have the global view about the entire network, which is similar to Google Maps. يعني أنا مثلا, if I ask Google Maps, okay, explain to me how to get from my house to QU, Google Maps can give you all the detailed information. Can tell you go out, go straight, go right, and then go left, and then go, and this will cost you this much, right? It will tell you that this street has this particular length, or you are expected to spend in this street this amount of delay, and so on, right? So it will give you all the detailed information. That's a global view, right? So this global view has to be constructed and maintained by every router in the network, such that all the routers, they will have the same link state table. So in step one, what we do is that we construct what we call link state table. This link state table, okay, is identical on all routers. So all routers, after exchanging all these messages, اللي هي بنسميها link states, they are supposed to construct the same link state table. Okay? And then in step two, we will have to run Dijkstra's algorithm, what we will discuss in a minute. Dijkstra's algorithm runs against this table and creates the routing table. In the routing table بقى, what I need to have in the routing table is if I want to reach to that particular node, I need to go through this hub. That's it, right? So, but the global view is maintained in the link state table. ماشي. The routing table has a destination address and next hop. That's it. Okay. So that's the global view. So if I ask any router how to go from one location to another, then the router can tell me everything from the link state table, right? But in terms of packet forwarding, it will have to use the routing table, which will tell the router to send a particular packet to one output port type. So that's global, right? The decentralized, or what we call a distant vector, is slightly different. We don't have to maintain this link state table at all, right? So what we need to do is to have each router will have only a partial view about the network. Each router maintains a partial view. And so this partial view contains, of course, the cost of the directly connected edges, for sure, because the router has this information by default. So when the router first starts, the router will have information about the directly connected links. So that's a partial view. But also, the router needs to have the total distance to any node in the network, but not the link states. هتقول لي ايه الفرق؟ هقول لك ايه الفرق. So we can explain that by an example. As we said, in the global view, we can ask the router how to go from our houses to QU, right? So the router would tell me go left and then go right and then go straight and this whole thing will cost you that much. So we have this global view from the link state table, right? For distant vector, the difference is you get outside of your house, you get to the first intersection, you find the router guy, okay? You ask that router guy, how do I get to QU? The router guy will tell you, go this way, and by the way, you have 10 kilometers to reach to QU. Okay? So if you ask that router guy, and then what? He will tell you, I don't know. All I know is the distance between me and QU is 10 kilometers through this node. But I don't know anything further than that. Okay? So you go to the next node, you ask the router guy there, so how do I get to QU? It will tell you, okay, so go to this direction, and by the way, the distance to QU is 8 kilometers, right? But then, what do? I don't know. فهمنا? This is the partial view. طيب, هتقول لي, طيب, this 10 kilometer and 8 kilometer, how would the router know that? The router would know that incrementally. So the router knows the distance between it and the next router, right? So it needs to know from this router, okay, the total distance to the final destination. Type. How would this router know? This router knows the cost of the directly connected link, and it will ask the next one. So the next one will have to ask the next one, and so on. So I always accumulate the cost in a distributed way, in a decentralized way, right? But I do not maintain any link states. I do not maintain a global view. واضح الفرق؟ I do not maintain any global view, right? So we will see that the algorithm that we will use for the case of the decentralized is totally different. Because if you have all the costs of the edges, right, Dijkstra's algorithm will allow you to construct what we call the shortest path tree to all the nodes, right? Because it has a global, based on the assumption that it has a global view. But for the case of distant vector, we do not maintain a global view, right? And we never maintain that global view in any way. We don't have any link state table, but we need to incrementally and in a distributed way accumulate the distances. We call it vector of distances. So we exchange vector of distances in a domain of one hub. That's it. ماشي؟ عشان كده بنقول إن هو إيه؟ local view or partial view. Right? طيب. So what are the pros and cons of each one? What are the pros and cons of global view versus decentralized? Of course, for the global view, I have to exchange lots of messages, right, in the beginning. صح? I have to flood the network with link states from all routers to all routers, right? Until I construct a global view at each router. And this global view is replicated in all routers. ماشي? Once I reach to that stage, خلاص, each router has all the global information. ماشي? But of course, as you can imagine, I have to flood extreme amount of messages until I can construct this global view. So in terms of communication cost, especially at the beginning, is really high. ماشي? Not only that, the storage for the global view is also very very expensive, because I have to maintain a link state table in addition to the routing table. So all routers will have to have storage for the link state table in addition to the routing table. تمام? So these are the disadvantages for the case of global view. But what are the advantages? The advantages is actually good, because once we construct the link state table, we can deterministically calculate the routing table in one shot, right? Once and for all, okay? And once we do this, we get into what we call a steady state, right? And we know that we have a steady state phase, right? We can deterministically know that. The problem with the decentralized is that because of the fact that you have a partial view, you don't know when you should stop. أنا دلوقتي بقول لك the distance between you and QU is 10 kilometers, right? How would you know that this is the best coast? I don't have a global view, right? So in a way, you are forced to keep exchanging these vector of distances regularly and periodically. There's no way for you to recognize a global steady state phase. It's very hard. It's very hard, right? So that's why in distant vector routing protocols, we have to keep exchanging these messages regularly, non-stop, almost non-stop. We don't stop, right? But as you can imagine, these messages, because they contain only a partial view or vector of distances, right? And they get exchanged only with the neighboring routers only, صح? So the number of these messages and the content of these messages is small. So the cost of exchanging these messages is small but continuous. In the case of link state, the cost is very high but short in terms of time. So I need to do it in the beginning. So it's like this. So the amount of messages for link state, it will be like, it will go up, right? In the beginning until I reach a steady state. And then it will go down drastically, okay? And it will only be like small only when an event happens, like مثلا a router goes down, a router comes up, things like that. And even then, I need to best communicate the event to have all the routers to update their link state table, and then خلاص, once they update their link state table, خلاص, they can run Dijkstra's algorithm again and construct the tree, right? So the cost is very high at the beginning, but it goes way down after this. صح? For the case of distant vector, it's like this. Of course, it's much less because I have to communicate partial view, right? And even the content of these messages is small, but I have to communicate them regularly, because I cannot recognize when the steady state will happen, right? So in terms of CPU consumption, of course, the length state is higher. Of course, the length state is higher, because every time you have to run the Dijkstra's algorithm, it's expensive, as we will see. It's expensive, and you have to run it from beginning to end to construct shortest path tree at every node. So each router will construct its shortest path tree, and we'll see how this is done, to all the other nodes in the network, right? Whereas for the decentralized case, we need to process only vector of distances that are coming from the neighboring router. That's it. And we'll see this is very light, but it has to be done in a decentralized way. So in terms of CPU consumption, it's less, because I have to process vector of distances in a partial view. Okay, so the amount of processing needed is not that much, but I have to keep doing that all the time. Type. So now we know the pros and cons for each one. So we need to talk about the length state, and in length state we have what we call Dijkstra's algorithm. Dijkstra's algorithm is shortest path. It constructs the shortest path tree, as we said, from one router to all the other nodes in the network. So how does Dijkstra's algorithm work? So the network topology, we have the nodes and the coast on the edges. So all the nodes, of course, and the coasts of the edges are available in the length state table. So we have this available. So that's the first assumption. And then we need to construct what we call least coast path from one node, which is the current router, to all other nodes. To all other nodes, from single source to all possible destinations in the network. And we will see one advantage of Dijkstra's algorithm is that we know the number of iterations needed, which is k, just such as k is actually the number of nodes, the number of destinations I need to get to. Okay? So we have deterministic number of iterations. We know the number of iterations. The worst case is that I have to have number of iterations equals to the number of destinations I need to get to. طيب, in order to do this, اللي هو assuming that حتى the number of destinations is n, so it's n basically, or k. ماشي? If we exclude the source node, yes. طيب, so in order to do this, we have to have some notations, and as we will see, Dijkstra's algorithm is systematic. It's simple, but it needs some practice. So you need to practice, and that's why I said that I will post some problems from the book, so just to allow you to practice how to run this algorithm. So of course we have the source node U, and we have different routers. So the idea is that at the beginning we have the coast between U and all the neighboring nodes. This coast is known, right? And usually it's finite. Okay? And then in the initial phase, U does not know the coast to the non-adjacent nodes. So it assumes by default that this coast is infinity, and hopefully the algorithm can improve this infinity to a lower number, which is the shortest path, or the shortest coast path. ماشي? So the coast by default is finite to all the adjacent nodes, and all the non-adjacent nodes, the coast is infinity. There is the distant vector, or dv, and dv is in fact the current value of the coast from the source all the way to a node V. Okay? So that distant vector is how we accumulatively try to maintain a course that hopefully after some iterations it will be the minimum distance or the minimum course. Okay? So we will maintain that vector of distances for all the nodes, and this will maintain the distance to the source, from this current node to the source, right? And we maintain the distance and the predecessor. This is very important. We maintain the distance and the predecessor. Predecessor اللي هو إيه؟ إن أنا this dv is based on PV such that PV is the previous node that will get me to the source. Okay? So I maintain dv and PV together. It's very important. Okay? And we'll see how this is done. Finally, we have what we call n dash. N dash is the nodes that are part of the shortest path tree that we are trying to construct. Okay? And in every iteration, we add one node to n dash. So we start n dash to have only the source node. So by default, n dash starts with the source node. And in every iteration, we have to add one node to n dash. So we know deterministically when to stop when n dash becomes a n. يعني when n dash contains all the nodes in the network. We stop. خلاص. Very easy. So the criterion to stop is very easy. Once n dash becomes n, we stop. واضح كده؟ طيب. Huh?
The next node, n dash means the next node?
لا, n dash is not the next node. N dash means n dash means that يعني we have to add this node to n dash, which means that this node is now part of the shortest path tree that we are trying to construct between the source node and all other destinations. Because the shortest path tree, as you can imagine, is a subset of the graph, صح? A shortest path tree is a subset of the graph that obviously does not contain all the edges, right? It contains subset of the edges. So when we say that this node goes to n dash, this means that this node is included as part of the shortest path tree. So we have to add the edge between this node and back to the source. ماشي؟ هنشوف يعني بالمثال يتضح المقال زي ما بنقول. we'll see how. اتفضل. And طبعا just to make it easy, we'll not go through this. We go through the example, and once we explain the example, this becomes very easy. So these are the systematic steps that we need to do. This is, of course, the initialization phase, and that's the logic that we need to do. The logic is very easy. Once we explain the example, this logic becomes very easy. And as you can see, but all we need to say here is that we have to do this loop, number of iterations equals to the number of destinations in the network. Okay? And once the n dash becomes n, this means that خلاص we stop. So this is the key step which we need to explain as part of this example. So this example shows that U is the source, and we are trying to construct the shortest path tree using Dijkstra's algorithm. Imagine that we have all the costs of all these edges in the link state table, and we just run Dijkstra's algorithm once and for all to construct the shortest path tree. Okay? So in step 0, what we need to do is that we have n dash initialized as U, which is the source node, right? And then we have to calculate the distance of all the nodes, right? So by default, of course, the predecessor to all the nodes will be U, right? So which means that if I need to go to V, okay, I know the cost to V, which is 7, right? And the predecessor is U. If I need to go to W, what I know now in terms of distance, what I know now is that to go to U, I have to incur a cost of 3, and the predecessor is U, right? If I need to go to y, y is not an adjacent node. So I don't know yet. Because all I have in n dash is just u. And to reach y from u is not possible. Right? To reach y from u is not possible. So I set it to infinity. Similarly to z. Okay? So the key thing here is that what you need to do is to select the minimum distance and add this node to n dash. Okay? So in the next step, what we need to do systematically is that we need to add this node to n dash. Once you add it to n dash, then you have to recalculate the distances in such a way that now you have two possibilities. Right? So you can reach any node in the network, either from U or from W. So you can calculate the vector of distances now based on knowing now U and W. Right? So in the next step, we need to add W in n dash. So now as a verification step for you, so all the predecessors here has to be included in n dash. If the predecessors here are not part of n dash, then there is a problem. ماشي? And here the number of steps equals to the number of nodes. Which means that if it's less, if it's more, then there is a problem. يعني some verification ways that you know that your work is correct. So now we have to add W to n dash. Once we add W to n dash, now we can calculate these vector of distances again, but based on knowing U and W. So for example, if I want to calculate the distance to V, okay, now I know that the distance to V from U is 7, but from W is based on the cost of W, which is 3 plus 3. So the minimum in that case is 3 plus 3 through this route. Okay? So once we, طبعا احنا when we add W, we add this link, and we'll talk about this later. Okay? So now if I want to calculate the distance to V, now the distance to V has improved to 6. ماشي? Also, once we add a node to n dash, we don't have to do any calculations for this node from now on. Okay? طيب. Next, the distance to x. I know that the distance to x is from U is 5. And from W, it's 3, of course, plus 4. So, of course, 5 is better. So, that's why it's kept as 5, and the predecessor is still U. It's not W. ماشي كده؟ And now بقى y, of course, to reach to y from U, it's not possible. The cost is infinity. But from W, there is 8 plus 3. Okay? So now, 8 plus 3 or infinity? لا, 8 plus 3. Right? So now it's 11. And the predecessor is W. But still, Z is not reachable from W, and it's not reachable from U. So I don't have to do anything, and it's still infinite. And now, in this step, which one is minimum? هتقول لي واحد يقول لي مثلا طب افرض I have two similar costs. Okay, which one do you select? Anyone, either one. ماشي? You select anyone, and it would still work. So here the minimum is 5, and the node here is x. So I need to add x to n dash. So in the next step, I need to add x to n dash, right? And now I have 3 possibilities. I can either reach any node, either from U or from W or from X. So what we are trying to do is we are trying to accumulate the nodes that maintain the shortest path back to the source. Okay? ماشي كده? So in step 3 we add X, and now we have to calculate all the distances. As you can see here, now Z has become reachable from X, and the cost is 14. Right? So now we started to see some cost on all the lengths, and of course the minimum here is V. So V is added to the shortest path. And when we add V, we have to add V from W because this is the predecessor. ماشي? And we keep doing that. Okay? So now the cost, so now we have to add Y. Y is the minimum, and we have to add it to the N dash. So when we add Y, of course, Z is becoming reachable from Y with the minimum cost. So Z is reachable from W with 3 plus 8 plus 2, or from Y with a cost of 4 plus 3 plus 3 plus 2. So the cost is minimum from predecessor Y. ماشي كده? So once we add Z to, because Z is the node with the minimum cost, once we add it to N dash, we stop. Because now we have all the nodes. And as you can see here, the red edges are part of the shortest path tree. And of course, as you can see, we have a subset of edges that, of course, does not contain all the edges in the graph. So this is the shortest path tree. ماشي? So from this shortest path tree, we can set the routing table. So for example, if I need to, so the routing table will be the destination address, which is the node. So now we have مثلا nodes X, W, we have V, we have Y, we have Z. ماشي? So if I need to reach to X, what is the next hub? It's this edge which will get me to X. If I need to go to W, it's W. If I need to go to V, what's the next hub?
From W6.
Right, so I have to set it to W here. Okay, so if I need to go to Y, W. I have to go to W first. If I need to go to Z, I have to go to W first. So this will be the next hub. Okay, and of course, the third one is the cost, which can be calculated easily based on this shortest path tree. So this is the forwarding table based on constructing this shortest path tree. Of course, the nodes here will be this will be destination addresses, IPs, and this will be the port numbers, يعني. Physical port numbers, يعني. مفهوم ولا في حاجة مش مفهومة؟ هو the algorithm is systematic, but it needs a little bit of practice. يعني once you do it once or twice, it will become very easy. Another quick example here, which explains the example that we just talked about. So if we need to construct from U, we need to construct the shortest path tree. So again, we'll do the same. We'll add all the vector of distances, and this is the minimum. So we'll add it to N dash, and then we calculate the distances, and we keep doing this. Okay. The important thing is that based on this, so we have to construct the shortest path tree, and the shortest path tree, like for example, for if I reach to V, I have to go direct. If I need to reach to X, I need to go direct, and then you will see something like this. This is the shortest path, or maybe like even this here. This is the shortest path tree that needs to be constructed based on these steps. In the initial step, you have to calculate the cost to all the destinations, right? And then once you calculate the minimum, in the next step, you have to calculate the distances to all except that minimum. ماشي? And then for each step, you have to reduce by 1, right? So based on that, you will have this shortest path tree, and then you will construct the routing table based on this. So the routing table is based on the next hub. So if I need to go to V, I need to go directly from U to V. If I need to go to X, I need to go directly from U to X. Otherwise, I need to always go through X. So all the other nodes, I need to go to X. So X will be the next hub for all the other nodes except V. ماشي? So any questions? Yeah, as I said, it's systematic steps, but we need to do it once or twice, and then it will become very easy. From here, right. So now we need to analyze the complexity of Dijkstra's algorithm. In fact, for Dijkstra's algorithm, the number of steps is deterministic. You can calculate the number of steps exact, right? So for example, at the beginning, if you need to reach to n different nodes, as you can. So if you need to know the exact number of iterations, so in step number 0, you have to calculate n different calculations, اللي هم equivalent to the n number of destinations, right? And then in the next step, it's n minus 1, right? And then it's n minus 2, صح? All the way to 1. حد مش فاهم ده جت ازاي؟ لأن in each iteration we have to calculate the minimum and put it in n dash, and then we don't calculate the distances for that particular node. So for each step we have to subtract one node. We don't do the calculation, or we don't calculate the distance for that particular node. So we keep subtracting by one until we reach to just one node. Once we add it to n dash, we don't calculate anything. So these are the number of calculations, right? So this is a sequential series, صح? So it's basically n over 2, 1 plus n, صح? So that's the total summation. Of course, in terms of O, all we need to do is to know that it's quadratic. يعني it's O of n squared. So this is the complexity of Dijkstra's algorithm. One thing to notice here is that, or one thing to note is that you can enhance, there is some improvement to Dijkstra's algorithm that can reduce this complexity to n log n instead of n squared. ماشي? We don't have to talk about this improvement and how it's done, but there is some improvement to Dijkstra's algorithm that can reduce this complexity even more. But what we need to discuss here is that one disadvantage in a length state algorithm in general, based on the minimum cost, is what we call oscillations. These oscillations is based on the fact that the cost on the edges is a real-time cost. This example is in fact a motivation why most of the dynamic routing protocols, I had this misconception that I always ask myself, why do all the dynamic routing protocols use offline matrix on the links? Offline matrix means what? مثلا the cost on the edge is actually the theoretical bandwidth of this link. But that has nothing to do with the real-time load of this link. صح? Because just the fact that a node, مثلا, let's say we have a node. This node has a theoretical bandwidth of مثلا 10 gigabits per second, which is very high, right? So which means that in terms of cost, the cost of this link will be very, very low, صح? The cost will be very, very low. So Dijkstra's algorithm will select this node very often. But selecting this node very often would mean that lots of traffic will go through this node, through this link, which will make the load on this link becomes very high, and that causes high probability of traffic jams. For example, if all the cars have the mindset that they need to go through the highway will not become a highway. The highway will become jammed all the time, صح? So I always ask myself, why do all the dynamic routing protocols, most of them, they use offline matrix and not real-time matrix? That's because of this issue. If you use real-time matrix, there is a possibility of oscillations. By oscillations we mean packet loops. ماشي. So this example here explains this by saying that if initially we want to send some traffic to node A, okay? Initially we didn't send anything. ماشي? Which means the cost on these lengths is zero. يعني I'm not sending anything, so there is no load, so it's zero, which means it's very, very good. The cost is very low, صح? So it's very good. Okay? So imagine if I need to send E units of traffic, and one from this node to A, and E from C to A, and one from B to A. Okay? So one from B to A, which means that after sending this packet and this packet and this packet, assuming that this packet will go this way, okay, the cost on this link will be E, because there is a E unit of traffic going from C to B, صح? And from B to A, we have E unit and we have one coming from B to A. صح? So the cost on this link will become E, the cost on this link will become 1 plus E. And from D to A, we have one unit, so that's normal. But after we send this is the current cost on this link. So if we need to send from B to A, now interestingly speaking, Dijkstra's algorithm will say, okay, so the cost on this link is 1 plus E, صح? What is the cost from B through C to A? So it's the cost of B to C, and the cost of C to D, and the cost of D to A, صح? The other assumption here is that the cost on the link is bidirectional, which means that the cost from this to this is E, but the cost from here to here depends on the traffic coming from B to C, which is directed, yeah. Which means that the current cost from B to C is zero. Okay? So now, if B wants to send this unit of traffic to A, it has two possibilities, either to go this way or to go this way, صح? What is the cost of this? It's 0 plus 0 plus 1, which is cheaper. صح? So here, it will say, no, I will send this unit of traffic through here because this seems to be cheaper. We see the problem here. The problem is that because of this real-time matrix, the cost on the lengths changes in real time very dynamically. And that causes the packets to A to oscillate from here to here to here to here to here to here. فاهمين اللي بيحصل؟ So now B will send this unit of traffic through here, and assuming that C as well will have two possibilities, either E plus 1, which is 2E plus 1, or 0 plus 1. So C as well will send it to this direction, right? And D here, it has the possibility of 1 or 0 plus E plus 1 plus E. صح؟ لا, إذا sending this direction is better. So which means that the traffic will go, all the traffic will go this way, okay, for a certain duration of time. But then what will happen? The cost on the other side is the cost on this direction is 0, right? So the nodes after, in the next iteration, they will realize that no, going through this direction is actually better. So it will keep oscillating from here to here. Okay? So this is the issue with real-time matrix. That's why routing protocols, they rarely use only real-time matrix. عشان بس ابقى دقيق. ها حد يفكر which protocol uses real time matrix partially؟ المفروض اجيب معاه شوكولاته ولا حاجه بعد كده عشان اللي يجاوب اديله طبعا انت comprehensive exam مسيطر عليك. So if you remember, EIGRP is the only dynamic routing protocol that uses real-time matrix partially and optional. يعني by default it uses offline matrix which is based on both the delay and bandwidth combined. ماشي؟ But it uses two other matrix as real time. If you remember, go to network 2. If you remember, two things: reliability and load. And reliability and load both are real time matrix. Okay? But you have to combine the cost between these four values. يبقى delay, bandwidth, which are offline, and two other, which is reliability and load, which are real time. And even these two real time are optional to avoid this particular problem. ماشي? So the assumption here is that even if you use the real time matrix combined with offline, this oscillation will not happen. Because if we don't use offline cost, the cost on the link will be zero, صح? Which will cause this problem to happen more probable and more often. Okay? But if I keep the offline matrix and add to it the real-time matrix, then this problem hopefully will not happen. واضح الكلام ده ولا كلام صعب؟ ماشي؟ Alright, so this is the problem with real-time matrix for the case of Dijkstra's algorithm or link state algorithm. For the case of distant vector, as we said, distant vector, they actually exchange partial view in the form of this vector of distances. Vector of distances. تفضل. ها؟ طيب فهو for distant vector algorithms, as we said, each node x, it needs to calculate the distance between it and y such that y is a final destination. كويس؟ For this, node x knows the cost to all the adjacent nodes. This is part of the partial view that I know. صح؟ So what I need is to get a vector of distances to the final destination from these adjacent nodes. ماشي؟ If I have these vector of distances from all the neighboring nodes, all I need to do is just to say that the distance between x and y is the distance to one of the adjacent nodes, and the cost I know, plus the distance between v and y. Okay? So I need to know all the possible combinations of the adjacent nodes and the distance between that adjacent nodes and the final destination. And in here, there's no بقى shortest path 3 or مفيش بقى global view. There is no global view. I need to construct the distance to only one final destination. Okay? So I need to calculate that distance based on the cost to the adjacent nodes plus the distance between the adjacent nodes and the final destination. ماشي؟ Assuming I have this, I can calculate all the possible combinations and select the one that gives me the minimum cost or the minimum distance. ماشي؟ طيب في هنا بقى حاجتين. الحاجة الأولانية, this distance, how would I know that this is actually the minimum? This distance to y is the minimum only if this distance between v and y is the minimum. صح؟ طب هو أنا do I guarantee that this distance between V and Y is minimum? This is the distance I got from the adjacent nodes, صح? I don't know if this is the minimum or not. It might change because I don't have global view. ماشي؟ So this is minimum if this is minimum. ماشي؟ Because I cannot guarantee that this is minimum. ماشي؟ I have to do this calculation many times. I have to do it regularly. ماشي؟ طيب حاجة تانية إن what happens the way that this protocol works اللي هو بقى for distant vector protocol, the protocol not the algorithm, the protocol itself, the way it works is through 3 different steps, but each step is very small and concise. يبقى the first step, receive vector of distances from neighboring nodes. ماشي؟ So this is step number 1. ماشي؟ Step number 2, calculate or calculate ماشي the current distances to destinations using البيلمان-فورد equation اللي هو ده بيلمان-فورد. ماشي؟ بيلمان-فورد equation. خلاص أنا عندي vector of distances coming from all the neighboring nodes. ماشي؟ Then I calculate the distance between me and all these destinations using this equation. And it's just one, it's not the algorithm, it's just one equation. بس خلاص one equation. بس أنا I need to calculate all these combinations and select the one with the minimum. ماشي؟ Number 3, if distance changes, then send to all neighboring nodes. Okay? So each node will calculate the distances to the destinations. ماشي؟ If that distance it changes, then خلاص يبقى معناها my routing table will have a change. Okay, so I need to change my routing table. Once I change my routing table, this means that I have to get the new partial view that I have and send it to all the neighboring nodes. ماشي؟ The neighboring nodes will have to be notified about the new values that I have. ماشي؟ So that's how you exchange this partial view, and because of the fact that you have no guarantees that these distances will be minimum at some point, we have to keep doing that. That's why most of the distant vector routing protocols, they keep exchanging these messages periodically. Like for example, مثلا in REP, these messages, they need to be exchanged every 30 seconds. Whether there is an event, there is no event, we have to keep doing that. Because we don't know when the steady state will happen. We cannot recognize that the steady state معناها ايه? Here, what is the steady state? The steady state is when I send these messages, the vector of distances, and then the answer to this question is always no. معناها there's no change of distances. The distances do not change. ماشي? And this will be no on all routers. If all routers reach to the same answer that there is no change in the vector of distances at all, this means that whatever exists in the routing table now is final. So that's the steady state. If one node has differences in these distances, then I did not reach the steady state yet. ماشي? And because I do not know, even if the answer for myself is no, maybe the answer for one of the nodes in the network is, the answer for me is يعني no, there is no change. I don't know whether there is one node in the middle that maybe it has differences in the distance, so I did not reach, or the network did not reach the steady state yet. ماشي? Because each node maintains partial view or local view, then I don't know whether I reach to the steady state or not. Therefore, I have to keep doing that all the time. ماشي? But as you can see, the calculation I need to do is not بقى ايه, it's not يعني complicated steps like case of Dijkstra وبتاع. لا, it's very simple. It's one equation وخلاص. ماشي? But what's really complicated here is how you exchange these vector of distances in a decentralized way. So ده بيلخبط شوية برضه, فهنشوف يعني hopefully برضه ده محتاج يعني ايه some practice in order to not to get confused and يعني miss on some of these steps. So similarly, we need to calculate this Bellman-Ford. So if I need to calculate the distance between V and Z, so between V and Z, ماشي? And this happens to be 5. ازاي between V and Z? Through here, 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 ماشي. ماشي. In any case, I received مثلا which node هنا? Node U. Node U received these vector of distances from V, from W, and from X. These are the neighboring nodes, V, W, and X. So these are the distances that node U received from these neighboring nodes. أنا أعرفش بقى these distances are calculated based on which nodes in the network. I don't know. I don't have to keep track of this because I don't have a global view. But I need to, based on this, node U needs to calculate the minimum distance to Z. So Z can be reachable from any adjacent nodes. So the cost between U and V plus the distance between V and Z. I have the distance between V and Z. So the cost between U and V is 2 plus the distance between V and Z, which is reported from node V, which is currently 5. So the cost between U and V plus the distance between V and Z, or the cost between U and X, which is another adjacent node, plus the distance between X and Z, and similarly for W is adjacent node because I have direct link between U and W, صح? So U and W, this is the cost between U and W, which is 5, plus the distance between W and Z, which is 3. So it happens that this cost is either 7 or 4 or 8. So all I need to do in that case is that to say, okay, so it's 1 plus 3, and in that case, I need to reach to that through X. So node U knows that the minimum cost to Z is 4, and to reach to Z, I need to go through X. After X, what do? I don't know. Node U does not know anything. Maybe it goes to X, and X will decide to send the packet back to U. I don't know. ماشي? I don't maintain any global view. And in fact, we'll see now a scenario where يعني it's similar to مثلا Waze. Waze tells you, okay, go to that street and you will reach in the minimum shortest time. So you go and all of a sudden you hit a construction. So after hitting the construction, you say, okay, so I will have to go back, ماشي, to the beginning of the street. What does way tell you? No, go here. I know there is a way. So you go back, you hit the construction again. It happens. And this is packet looping, and it happens in this decentralized routing algorithms a lot. It happens, and we'll see that scenario. So after X, I don't know what will happen. I don't have any global view. ماشي كده؟ So the distant vector routing protocol, we need to estimate the least cost اللي هو the distance between any two nodes x and y, and we calculate that iteratively, but in a way that we do not deterministically know when do we end. We don't know. ماشي? So from node x we can calculate the distance based on the minimum cost from any adjacent node. Okay, so this is basically the Whiteboard equation. So we'll have to go through an example just to illustrate this. So the basic idea is that from time to time, and here by from time to time, D is underlined. From time to time. يعني as I said, rep يقول لك 30 seconds. EIGRP يقول لك sometimes every 5 seconds, sometimes every 30 seconds. But if there is an event, we send immediate up. يعني there is بقى إيه عشان كده from time to time. But you have to keep doing that. Each node sends its own distant vector estimation. عشان كده it's an estimation. We don't know if this is. Our estimate is that this is the distance, but we don't know if this distance is the minimum. ماشي? When X receives new distant vector estimates from the neighboring nodes, it needs to apply Bellman-Ford to know the minimum cost. But this minimum cost is, again, it's another estimate that we don't know whether this is globally minimum or not. So this is minimum based on the partial view that I have. Now, is it the global minimum? I don't know. واضح؟ ماشي؟ Under minor natural conditions, the estimate of dxy converges to actual least cost. This is the hope. This is the hope that through doing this few iterations of time, which we don't know the count of these iterations, ماشي? At some magical moment, we will logically reach to a state where whatever distance, vector distances are exchanged, I never have to change my current distances based on the information I receive. The answer is always, I don't have to update the routing table, which means I don't have to exchange the vector of distances again, which will have the same result on all the routers. When this happens, then we reach the steady state case. ماشي? So let's see before that, one characteristic here which is very important. As we said, it's iterative, but we don't know the number of iterations here. We don't know when we reach to the global minimum. But another characteristic which is very nice and very important, it's asynchronous. يعني asynchronous. يعني I don't have to wait for getting all the vector of distances from all the neighboring nodes in order to run Bellman-Ford. يعني I can decide at any moment based on receiving the vector of distances from one node, from two nodes. Okay? But Bellman-Ford guarantees that you will always improve. You will always go through improvement and you will never go through degradation. ماشي؟ Which is a very nice feature. ليه بقى هو بيقول لك يعني asynchronous is good? Because guaranteeing synchronization is in a decentralized way is always very hard. Is always very hard. Why? Because the nodes by default they use different clocks, they use different transmission rates. Okay? So if you have to wait for all the neighboring nodes to give you the vector of distances every time, then you might have to wait for a very long time. Okay? Because the nodes by default, they use different transmission rates, they use different, because the lengths are different, are heterogeneous, are different, right? And if you need to have يعني synchronized time when to perform this synchronized time is based on which node? Because all the nodes, they use different clocks. So synchronizing these clocks between يعني distributed nodes is always very hard. Right? But the beauty here, or the good thing about Bellman-Ford, is that it can be done at any point of time. Okay? When you receive one vector of distances from one node, you can apply it. You receive two vector of distances, you can apply it. ما فيش مشكلة. You will always go towards improvement. Okay? يعني you will always converge and not diverge. You will always go through convergence and not divergence. ده المهم. In all decentralized algorithms, we always want to guarantee that there is no divergence. Divergence معناه ايه؟ And sometimes we improve, sometimes we degrade. So if that's the case, then we go through oscillations and we'll never reach to the steady state. Whether we can realize the steady state or whether we cannot realize the steady state. But we can go up or down, we keep going up or down, we oscillate and we never converge. So that will not happen using Bellman-Ford, which is very, very important. Even if we do the calculations asynchronously, which is very important. ماشي كده؟ And it's distributed, so each node notifies the neighboring nodes. يعني خد بالك بقى هنا. Each node is only responsible to send the vector of distances in a domain of one hop. That's it. ماشي؟ And link states, I need to report the states of the links to all the nodes in the network. I need to flood. لا في فرق بين broadcast و flood. Broadcast means برضو ان انا broadcast to the nodes neighboring to me. انما broadcast does not necessarily mean to all the network. عشان كده هم بيسموها flooding. Flooding معناها each link state has to flood to the entire network. يعني it has to go through multi-hop to every node in the network. Okay. So I wait for a change, recompute using Bellman-Ford, and if the node changes, I have to notify neighbors. These are the 3 steps that we talked about. So that's the example. And you can see, you can imagine this example is only for 3 nodes. طبعا, if we have more than this will be much more complicated. So the calculation itself is very simple. It's based on Bellman-Ford. But because of the fact that we have to do that at every node in a distributed way, and every node has to exchange vector of distances to all other nodes, that's what makes this a little bit يعني not complex, ولكن it needs some focus in order to follow the steps. And because it's iterative, it's very important to pay attention to the time aspect. So that's at time t0. So at time t0, this is the initial state. The initial state is that each node knows the cost to the adjacent nodes only. And it does not know the distances to all other nodes. ماشي? So for example, here at time 0, x knows the distance to itself, which is 0 by default, knows the distance to y, which is 2, and knows the distance to z, which is 7. ماشي? طبعا if there is a node here, مثلا, this node مثلا, let's say w مثلا, okay, and I don't have direct connection to it, and I add w here مثلا, what would be the cost? X, what would be the cost to w? Infinite. بالضبط. عشان بس يعني ايه. Okay, طيب. Similarly, y knows the distance to x, which is 2, and to y to itself, which is 0, and to z, which is 1. Similarly at z. ماشي? So the idea بقى هنا إن at time t1, node x will have to receive the vector of distances from y and the vector of distances from z. So these 2 rows, okay, will have to go here, ماشي? And based on these two rows, now I need to recalculate this. For example, the cost to y, okay? The cost to y is either to go directly to y, which is 2, or maybe y will give me another distance which will reduce that cost even more. ماشي? So either I have 2 plus 0, or maybe مثلا 7 plus 1, which is obviously more. So the cost to y will still be 2, as we can imagine. But the cost to z بقى, the cost to z, okay, this is the one that will probably change. So at time t1 بقى, so we have the vector of distances from y and from z, okay, and we have to calculate the new cost between x and all other nodes based on these vector of distances. ماشي? So as we can imagine, so to calculate this is in fact either 2 plus 1 or 7 plus 0. So in that case it's 3. ماشي? So that's why this one is updated to 3. Same thing بقى goes to y. Y will receive all the vector of distances from x and z, and z will receive the vector of distances from x and y, and so on. ماشي? So that's how يعني the vector of distances will change, and for everyone I have to keep updating these vector of distances based on the distances which we receive from the neighboring nodes. The idea here is that in 3 iterations here, logically I have reached the steady state, which means that all the costs in this matrix will never be better, which means that we have reached the steady state. We can see that now because we have all the numbers, but for the view of each node, the node doesn't know, so the node will have to assume that we have to keep يعني sending the routing table periodically. ماشي؟ طيب. One thing here is that يعني if بقى in this scenario, if a node changes its cost, ماشي؟ يعني مثلا from this router to this router, instead of having wireless link, now we decided to have wired link. So the wired link has higher bandwidth, and now the cost has reduced from 4 to 1. ماشي? So now, when I change the cost on this link, node Y will detect it, and node X will detect it. صح? Both routers, they will detect it. The assumption here is that node Y will detect it first. But before this, let's keep in mind that Y will have to it receives the vector of distances from Z and X. Okay? So Y will receive the distance from Z to X as ايه بقى؟ ده اللي مهم. What is the distance between Z and X? What do you think? Huh? برافو عليك. It's 5. It's 5. It's not 2. ليه بقى؟ Who detected the link cost change? Y. Z cannot detect that. So Z still in its table, in its distant يعني vector, that the cost to X is through Y, and it's 5. So Z يعني the vector of distances that Y has is that dZX is 5. But it has dy x equals to لا خد بالك dy x صح يا 1 صح بس either it's it's cost of y x plus the cost plus the distance between x and x, which is 0 طبعا, or the cost between y and z, صح, plus the distance between z and x, صح? So this is a, so the distance between y and x is 1, صح? And the distance between y and z is 1 plus the distance between z and x, which is 5. 5.
This one is 5.
صح? 5. Okay? So the distance between y and x will be 1, صح? So y will update its distance to x as 1, and z will, طبعا when y detects the change in the distance, what will it do? It will send that vector of distance to z and x, صح? And this happens in here. So z receives the new vector of distances from y and from x. So now z will have the information in the next time step that the distance between y and x is 1. صح? So z will say that now, instead of the distance between z and x, which is 5, I have by now the distance between z and x is either the cost between z and x, which is 50, or the cost between z and y, which is 1, plus the cost between y and x, which is 1. صح? So isn't the new cost will be 2 instead of 5. طبعا the distance here changes. So z will send back to y the new distance, which is 2, and we have reached the steady state because يعني خلاص يعني, so in after t0, t1, t2 خلاص we have reached. So in 3 iterations everyone will be happy and I have reached again the steady state. In other words, good news, they travel fast, but still we had to go through 2 iterations to stabilize everyone. But the idea here is that because this link got better cost, this will not change the next hop for any other node, because we only have a node that has now a lower cost. Okay? So good news, travel fast, because having a link with a better cost will not change the next hop for all the nodes in the network. But we just need to report the new distances, and that takes 1 or 2 iterations and everyone will be happy. So that's the explanation of good news travels fast. ماشي? So this is the issue that يعني related to the decentralization of the algorithm. And I cannot go through the next time now because I think يعني you are خلاص you are saturated. فيعني tomorrow or next time inshallah we'll go through this example, which is a bit tricky because of the fact that good news travel fast. We'll see that bad news travel very, very slow. We'll see بقى how slow بقى. يعني this بقى scenario will have to go through loops and we'll have to go through messages back and forth, which is the issue of count to infinity, if you remember in network 2. So here we have to analyze it from a complexity point of view. We have to calculate the number of iterations until we get to the steady state, which will have enormous implication on the control messages that get sent and on the packets. Packets will get into loops. The vector of distances will have to go back and forth for tens of iterations until we reach to the steady state. Okay, and then of course we'll talk about some يعني technique that we can use to mitigate these loops. I will talk about it next time, inshallah.